will recall from part 1 on electricity that electricity comes in two forms. First, real particles of positive and negative electric charge. And second, waves of instant electric energy. Many electrons in metals exist in a sort of sea of electrons, like chocolate chips in a cookie. When we force that sea of free electrons to move, that is when the electromagnetic energy field appears. In segment 11 of Electricity and Magnetism, we continue our discussion on that electromagnetic field by looking at common household outlets and circuits and answering this common electric question: why do electric outlets look like little surprised faces? If you live in the United States or Canada, have you ever noticed how an electrical outlet looks like a little surprised face? With one eye bigger than the other and a big open mouth. If you add a mustache, it helps. Now, if you installed them like this, upside down, you don't see the face so much. The U.S. Electrical Code doesn't specify which way to put them, so sometimes you will see them inverted. But if you live in Australia or New Zealand, you have outlets that look kind of empathetic, like they're saying, "Oh, are you okay?" In Italy, they just have 3 holes looking like a traffic light. And Denmark probably wins the award for the world's cutest looking power outlets. But the common feature in all of them is 3 holes. And why 3? The answer goes back to 1880 in a power war between Nikola Tesla and Thomas Edison, often called the War of the Currents. Edison managed to perfect a light bulb filament and make light bulbs at an affordable price where everyone could buy them. But the real money was in supplying the electromagnetic energy which the light bulb would convert into heat and light. Edison built the first electric power station in New York to supply this energy, and he used DC, direct current power, to do it. The problem? DC voltage couldn't travel very far. Edison's solution was to put a money-making power station on nearly every city block. Tesla, who at one time worked for Edison, left Edison's employment and joined with Edison's main rival, George Westinghouse. There he patented a new distribution system where a small voltage could be stepped up to large voltage for very long-range transmission, then stepped back down again to small voltage when it got to the homes. No need for all of Edison's power stations. It was called alternating current, or AC, and a marketing war broke out between the two rivals, the War of the Currents. To win the war, Edison began a negative media campaign to discredit Tesla and Westinghouse, even going as far as having his workers publicly electrocute animals using alternating current in order to convince the public that it was unsafe. If an animal or even people were killed by AC electrocution, Edison would publish that they had been Westinghoused. Ultimately, Edison both won and lost. He lost because in spite of his negative marketing campaign, alternating current became the permanent distribution system for electric power in the United States. But he won the marketing war because Edison's name was permanently associated with power distribution, whereas Nikola Tesla was thought of as an odd, eccentric genius when he was thought of at all. When you look outside on the telephone pole, you are looking at Tesla's alternating current wires running long distances to your house. You also see that there are glass or ceramic insulators keeping the voltage from touching the telephone pole, grounding there, and then electrocuting you. You also see these big cans. These are Westinghouse type transformers stepping down the voltage before it goes into your house. The very presence of all of these long power lines throughout the country and your community are a demonstration of how AC won the war of the currents. Ironically, all of our computers run off of Edison's DC, and the alternating current must be converted to DC before entering the computer. In this new house, you can follow the wires to where they actually originate. They go from the outlet, up the walls, and into the main power panel in your house. The 2 or 3 main wires go out of your house to the power pole, then follow miles of wire to a distribution station. The wires eventually find their way back to the power generating station where we find pumps, charge pumps, whose sole job is to create an imbalance of charge by spinning a circle of magnets around a coil of wire. Then pump that imbalance so that the magic electromagnetic energy wave appears and travels down the wire to the outlets in your home. The generator may be at a coal-fired plant, or a nuclear plant, or a dam, anything that will cause the generator to spin the magnets around the coil of wire, and that action pumps electrical charge. Those big generators are, in a very real sense, in constant contact with all of the appliances connected to them. They are essentially aware of everything that is using their voltage. The fuel in this model is boiling water, which makes steam. The steam shoots over the turbines, causing them to spin, just like the falling water over the dam made those turbines spin. The turbine is connected to a generator which spins magnets around a coil of wire, pushing charge and creating the electromagnetic energy wave. The black dots represent the slow-moving charge, and the yellow represents the fast electromagnetic energy wave. Whenever you turn on a light bulb, the electric company's generators feel it almost instantly. Your light bulb uses up some energy. As a result, the generators start to slow down a tiny bit, and more fuel must be burned in order to prevent this. By turning on a light bulb, you can cause a distant nuclear reactor to consume a tiny bit more U-235 fuel, or cause a coal-fired boiler to grind up a tiny bit more coal into powder for burning. On the other hand, when you suddenly turn off a light, you create a dead end in the energy system. The energy that was sent into your home starts being reflected back to the big generators, and it makes them spin a tiny bit faster. The electric company computers automatically turn down the fires a tiny bit, which run the steam turbines to keep the generators from speeding up. Now, this copper wire does not have electrons and protons inside of it. It is made of electrons and protons, so many and so small that we couldn't possibly show it. But for illustration's sake, let's just say that we can look inside and see a few of them. This is a copper atom, and these are some of the trillions and trillions of free electrons sitting here like chocolate chips inside a cookie. Many people think that in electricity, it is the free electrons that move at the speed of light inside the wires, but this is not the case. In Edison's DC system, direct current, which is what batteries use, the forward movement of the physical electron charges is about the speed of slow molasses, like a snail in the wire. In fact, in Tesla's AC, alternating current, the charges hardly move forward at all. They just sit in the same place and alternate back and forth, wiggling and generating the fast-moving electromagnetic wave. This is similar to how water molecules stay in roughly the same place even as the wave of water energy surges forward. See, the duck and the water bubbles don't move forward. They just sort of alternate back and forth, bobbing up and down. It is the energy wave that is rapidly moving forward. Likewise, in electricity, as the electrons wiggle back and forth in AC, or slowly creep forward in DC, it is the wave of electromagnetic energy that surges rapidly forward along the wires. The original outlets had only 2 holes in them, the same as the top 2 holes in a modern outlet. Now, you probably think that these holes represent 2 different wires, but in reality, there's only one very long wire connected in a long circle. Bicycles are powered by your legs, moving a chain-driven sprocket, moving in a continuous circle. Like any chain and sprocket, when one link moves, the entire chain moves together. Completed electrical circuits are similar. Move one electron, and like the chain links, they all move almost at the same time, a sort of chain reaction. And they move at the same time because they are negatively charged and they repel each other, just like trillions of little magnets. Push one and they all repel one another instantly all the way down the chain. Now, if you look closely at the chain right at this point, it actually looks like 2 chains moving in opposite directions, similar to how the electrical outlets look like there are 2 wires. But when you see the whole picture, you see that it is actually just one long chain moving in a continuous circle. Completed circuits in your house are like this chain, moving in a circle, beginning and ending with a power station. The electric company doesn't sell electrons. It pumps the electrons, which are already filling the wires, and sells the energy created when the electrons move. Many cities have taxi bicycles, and you can pay for a ride. But of course, you don't pay for the chain. The driver keeps the chain. You pay for the energy the driver supplies by pumping the chain in a circle and giving you a ride. Just like the electric company, you don't pay for moving electrons. The electric company keeps those. You pay for the energy they supply by pumping electrons in a circle. And how can we pump electrons? We will cover this more in segment 13, but briefly, every magnet creates a magnetic field. The free electrons inside of a metal will just randomly move about, but cut across the field with a wire, and it forces the electrons to drift in one direction. Cut across the field over and over by rotating it, and you pump electrons. You can also use chemicals in a battery to force a charge imbalance and pump electrons. Here is a simple electrical circuit using a battery, Edison's DC power pump. The battery uses chemicals to cause a charge imbalance between the negative terminal down here and the positive terminal up here. We call a charge imbalance voltage. If you connect the two ends together with a single wire, charge will begin to move and generate an electromagnetic energy wave that will heat the wire and the battery very rapidly. You can even start a fire in the woods using a thin wire or even the foil from a stick of gum. Cut a strip from your foil gum wrapper. A gum or candy wrapper is needed as it has paper on one side and very, very thin foil on the other. Regular foil is probably too thick and you might end up catching your battery on fire. You are, after all, dead shorting the battery. Fold the paper in half and cut it at an angle so that this end here gets very thin in the middle. Connecting any battery will force a charge flow, current. Pinch the end so it doesn't tear on you, then connect your battery. Where the foil is thinnest, it will heat up and make a small fire. You can use that to ignite the kindling of your campfire. You can also start an emergency fire by touching a 9-volt battery to fine steel wool, since the steel will complete the circuit and cause heating. Remember, shorting a battery causes a flood of electromagnetic energy, and if there is not a proper load or a way for the energy to dissipate, the energy will probably cause a thermal runaway and catch your battery on fire. Normally, you don't short out a battery like this with a wire, or a 9-volt battery directly with a wire. But if you put a device in the middle, like this light bulb, they call it a load, and some of the battery's energy will convert directly into light and heat. We touch the light bulb directly to the battery, but you could add wires to extend it. Notice here, one wire, starting here, going through the light bulb, to the other side, back to the battery. This is called a complete circuit, and it only takes, really, one wire. You could have a very complex circuit with lots of bulbs and fans and switches and pieces of wire all together, but ultimately, it's just one wire connected from one side of the battery pump and ultimately going back to the other side of the battery pump. The reason there are two holes up here is to connect the single wire together. We complete the wire by putting some device on it, just like we put the light bulb in our current, and it completes the wire. Every outlet in your house represents the meeting of the negative side of a battery or energy source to the positive side of a battery or the energy source. Remember, the wires are made of electrical charges. The charges are already in the wires and are waiting to be pumped by a voltage imbalance. The charges are represented here by the little dots. If you just connect a wire here, you will open the floodgate of energy and burn out the circuit. But by connecting a load like a motor or a light bulb, the load is designed to convert the electromagnetic energy wave into light, or, in the case of a motor, into motion. You will recall in the segment on thermodynamics that nearly all of the energy on Earth comes ultimately from the sun. And so it is here. The sun evaporates water, which falls on the mountains, which runs to the dam, which rushes through a turbine, which turns magnets in a coil of wire, which separates and pumps charges, which produce an electromagnetic energy wave which then travels at the speed of light to the light bulb in your home. From there, it is converted back into heat and light, or motion, in a motor. The power stations and the national power grid do not store the energy they create. As a result, the energy you get when you switch on a light was created at a faraway power station less than a second before. As a result of not storing power, they must constantly balance the right now demands of electricity from your house with the right now generation of energy at the dam or power plant. Electricians call one of these slots in the top the hot and the other one neutral. Now, if you stuck a wire into the two top holes, it would complete the one-wire circuit. But appliances and a light bulb called a load converts the amount of electromagnetic energy that goes through it. If you just stick a wire in between there, you immediately open the floodgates of electromagnetic energy, and you'd probably get a spark and a bang and fire and maybe electrocution. For outlets in North America, the hot wire is connected to the little eye. The hot carries the voltage. The wider slot is the neutral wire, which is at 0 voltage, the same as you and the ground that you stand on. That's why if you touch the bare wire in the neutral, nothing happens. You are both at the same voltage. But if you touch the hot, it is at a much higher voltage than you are, and you get a significant shock. By the way, this tells us why birds do not get electrocuted sitting on power lines. As long as both of the bird's feet are on the same wire, either the neutral or the hot, the bird is safe because it is at the same energy potential. The voltage remains the same between the wire and the bird. But if the bird has one foot on a hot and its wing or its other foot touches, say, the pole, which is grounded, the current finds a fast way to balance the huge voltage difference by going through the bird to the ground, and the bird is electrocuted. The same thing would happen if the bird's wing hit the opposite neutral wire while it was standing on the hot. The bird becomes a fast conductor for high voltage. This is why you will often see very tall insulators to separate the wires in areas where there are birds with wide wingspans. But what does the frowny face part do? Well, it actually doesn't do anything. The circuit is complete without it, and your appliances run just fine without it. It's actually there as sort of a reserve parachute, just in case something goes wrong. A safety parachute is a backup parachute that you can use if the first one fails. It's kind of in the way and you really don't need it to go skydiving, but if something goes wrong, it'll make your day if you have it. The ground is an electrical safety parachute. If the hot wire should break and accidentally touch the metal case of, say, a toaster, then touching the case would be the same as touching the hot wire directly. you get a shock. And if you're standing in water, it could easily be fatal. So manufacturers attach a third wire, the grounding wire, to the case, and this is the third prong on a plug. The ground wire is actually the little frowny face right here. When the wires come from your house, a green wire is attached to this green screw here, and that's the ground. The frowny face grounding wire goes straight to the grounding bar, which is in your power panel. The grounding bar itself is then attached to another ground, usually a metal rod or a spike driven deep into the earth. Or sometimes a ground can be attached to a water pipe, as a water pipe makes for a good ground. Take a look around your house, and you will usually find the grounding spike somewhere near the outside. In fact, every single power pole in the US has a grounding wire attached from the neutral line, or the transformer, directly to Earth as its safety parachute. In addition, the power panel in your house is filled with circuit breakers. The circuit breaker will trip off if there is a short in the circuit, safely cutting the current off from the wires. Sometimes a safety fuse is used. The fuse is made of wire that just barely handles the current going through the other wires, plus a tiny bit more. But if there is a huge surge in current, the fuse burns out, disconnecting the power to the wires, and the device turns off. Many appliances in your house do not have the third grounding wire. Instead, they make the case out of non-conducting material, like plastic, and use 2 layers of insulating material around the live parts. Such devices are often called double insulated and must pass strict electrical safety tests before being sold. So the 2 eyes of an outlet represent the hot and the neutral, and when something is connected to them, they represent the continuation of the single wire that makes up the circuit. The frowny face is the ground, the safety parachute that helps keep you from getting electrocuted in case of a short. So here is power transmission in one look. After generating the voltage at the power plant, the electromagnetic energy wave travels down high voltage transmission lines, often carrying 500,000 volts or more from Tesla's vibrating alternating electrons. This can be transmitted about 300 miles, where it goes to a substation that steps down the voltage to about 10,000 volts and splits it into different areas. Telephone and cable companies often use the same power pole for their wires, which you can see mounted lower on the power pole. The voltage usually then enters a neighborhood substation to reduce the voltage again, so it can travel on the lines to your neighborhood. At your house, the voltage must again be reduced by entering another step-down transformer on the pole by your house. Or, if you have underground power lines, you will see a pad-mounted transformer. The electromagnetic energy wave is now at a voltage that can be safely used in your home. The lines that connect to your house are called the service drop, and it is usually made of a set of 3 twisted wires, 2 insulated 120-volt wires, and 1 neutral wire. These go directly into the electricity meter, which records the amount of energy you use. The power company reads the meter every month and charges you for the amount of electricity you used. From the meter, the lines go into the circuit breaker panel, and you can see the 2 primary wires, the 2 120-volt wires here, and the neutral wire here. Those are the wires that came from the transformer on the power pole. The main circuit breaker is here at the top and lets you cut power to the entire house when needed. The wires then split off into the different rooms or areas of your home, and each one has its own circuit breaker. If the circuit breaker is on, the power flows through the wires in the wall to the final destination, usually an outlet or a light in a room. Most outlets use only one of the 120-volt wires, except for your dryer, which uses both to run the heater that gets your clothes dry. Notice that the dryer outlet looks like this huge 3-pronged device so that you will not mistake it for a regular 120-volt plug. All devices use energy, and we have a common way to tell how much energy each device uses. For example, this electric heater will unwind energy at a much faster rate than this digital clock. They both use energy. They both unwind power. But this one uses much more than this one. We needed a common way to tell how much energy each device was unwinding. A bucket full of charge is called a coulomb. If you poured 6.24 quintillion negative charges into a bucket, you would have 1 coulomb of charges. 6 quintillion is 6 times 10 to the 18th power, or 6.24 billion electrons, which is roughly the same number of sand grains on the entire Earth, including every land area, every ocean, and beach, and desert. Now, that is a huge number, but it is a tiny, tiny submicroscopic bucket because the electron charges are so very small. Way, way smaller than the eye of our needle, but you get the idea. A tiny bucket of 6 quintillion charges is called a coulomb of charge, named after the French scientist Charles Augustin de Coulomb. 1 coulomb is a pile of real physical electron charges. We can measure how many coulombs per second flow. We measure how many tiny buckets flow by every second. When charge begins to flow, that's how we measure it, by the second. How many coulombs are going by every second? The more coulombs per second, the more energy you produce. 1 coulomb going by every second makes less energy than 15 coulombs flowing by every second. When charge flows, we measure it in coulombs every second. A typical outlet in your house supplies about 10 or 15 coulombs per second. You could probably run 2 average light bulbs off of this. If you take a tiny wire, maybe it will handle only 2 coulombs every second, whereas a much bigger wire will handle 15 or 20 coulombs every second. Similarly to these straws. With this one, I get 1 coulomb per second through, but this one I get 10 coulombs per second. Remember in the section on heat? We found that James Joule discovered that work and heat, or work and energy, are interchangeable, and as a result, all forms of energy are measured in joules. Well, electrical energy is also measured in joules. We measure charge in coulombs, and when coulombs are moving, we measure it by the second. Likewise, we measure the electromagnetic energy in joules, and as the joules move, we measure it by the second, joules per second. So, how much electromagnetic energy will this heater convert into heat every second? How many joules per second? There's actually a fairly easy way to calculate that, but that's not what we're interested in right now. Based on James Joule's work, we can calculate that this heater is using 2,400 joules every second. That's a lot of joules, especially when you consider that 1 joule of energy is the same amount of energy that it takes to move this apple from here to here. That was 1 joule of energy. And this machine unwinds 2,400 of those every second. On the other hand, this clock here uses only 4 joules every second. Much less energy than the heater, but still up and down every second. I'd hate to do that all day long just to get my clock to work. It sort of gives you an appreciation for just how much energy is produced every second just to have the things in your home run. You now have a pretty good idea that when you turn a light on, it uses many joules of energy every second. But not all devices are equally efficient in their use of joules. For roughly the same brightness, this older incandescent bulb uses about 60 joules of energy every second. This compact fluorescent uses only about 15 joules per second, and this LED light uses only about 6 joules per second. The older lights convert most of their joules per second into wasted heat, and only a small percentage is converted into light. By the way, we've talked about 1 coulomb per second flowing for matter, charge, and 1 joule per second flowing for energy. These terms were soon given shortcut names. Charge is positive and negative atom particles. 6.24 billion negative charge particles is 1 coulomb of charge. And when charge flows, we call that an electric current. And we measure that current in coulombs per second. Coulombs per second was given a shortcut name after the French physicist André Marie Ampère. 1 coulomb per second is called 1 ampere, or 1 amp for short. And electromagnetic energy is measured in joules. When electromagnetic energy moves, we call that electric power. And we measure power in joules per second. 1 joule per second was given a shortcut name after the man who perfected the powerful steam engine. 1 joule per second is called 1 watt, after James Watt, the Scottish engineer. And to force charge to flow, you need to imbalance the charges. Charge imbalance is named voltage, after the Italian physicist Alessandro Volta. 20 coulombs per second is 20 amps. 60 joules per second is 60 watts. Voltage, amps, and watts.